All right, so section 12.5, day 1, we're going to start looking at equations of lines written in vector form and written parametrically. Up to this point in your math careers, you might have done a little bit of this in pre-calc, but the first way you ever learn how to graph a line or write the equation of a line would be in point-slope form and in slope-intercept form. If you're given any point on the line and you're given the direction of the line, which would be represented by the slope, m, as long as you have a point, we'll call it x1, y1 on that line, and you know the slope of that line, m, you can write the point slope form of that line. So a little bit of a throwback to algebra 1 here. Y minus y1 equals slope m times x minus x1. Okay, that's your point slope form. Now, how do we do this parametrically? Let's say that we're working with a line in R3, in three-dimensional space. And we know some point on that line, let's call it P naught, which is represented by X naught, Y naught, Z naught. And so I'm going to highlight that point on the visual so you can see that. There's P naught. And another point on the line is more generally given as P, which we're going to call X, Y, Z. Well, as long as we know an initial point on the line and we know the direction of the line, so if we can find a way to express a direction vector that goes from P naught in the direction of P, which is going to be the green. Actually, I'm going to pick a darker color. Let's do blue. I want to get from P naught, and I want to move in the direction of P. Okay, so we'll call that vector A. As long as we have a direction vector and a point on the line, we can write the vector equation of the line, and we can write the parametric equations of the line. So, as I mentioned, let's let P be some arbitrary point on the line given by X, Y, Z. And what we're going to do is we're going to connect vectors to the initial point and the terminal point. So I'm going to call this one here, R sub 0 is going to go from the origin to P naught. And so that vector could be represented as O P naught. And if I connect another vector, I'll do this one in, pick a new color here. Let's do maybe a darker green. If I connect a vector from the origin to that final point, that arbitrary point P, that would be represented by OP. Well, and then what we really want to focus on is that vector A, because that vector A is moving in the direction of the line. Well, the vector representation for A, if we think about what we have here, focus on the little triangle setup we have. We have R sub 0, we've got this vector A, and then we've got this vector R. If we think about our tip to tail vector addition that we learned about a couple sections ago, A is the vector with representation P naught P. And if we do our vector addition here, the pink vector plus the blue vector working tip to tail would give us the green vector. So R sub 0 plus A would give us R. And notice, take a look down here. I'm going to draw this vector in blue also. We have this vector V, which is parallel to A. If I shift that vector V up and I start to scale it, it's moving in the same direction as A, which is on the line. So since A and V are parallel vectors, we know from last section, there exists some scalar t, some real number, such that the vector A is some scalar multiple of the vector V. That's what it means for two vectors to be parallel. So putting it all together, if we look at our little equation that we created here, then if I rearrange R0 plus A equals R, I would get R equals R sub 0 plus, we said that A is equal to a scalar multiple times V. And so we can substitute in TV for A. So this right here would be our vector equation of that line. Okay. And every single value of that parameter t is just going to end up giving you a different point on that line. So maybe if I pick a positive value of t, put a point on the line there in red, well, now I'm going to end up out here if I was to connect my vector r. But what if I pick a negative value of t? Well, maybe I end up here on the line. And so I can connect a vector to that point. So you can end up getting this vector function, which basically connects from the origin to every single point on that line. And then you end up getting the span of all of those points ends up giving you the line, which is represented by this equation. Okay. So all of these are just different values of r based on the value of t that you choose, which ends up giving you the entire line. Okay, so what we really want to be able to end up doing is, given a specific point on the line and given a direction vector, we want to be able to write that equation. Well, let's use the fact that r is equal to vector x, y, z, and r sub 0 is equal to vector x naught, y naught, z naught. Then if the vector v that gives the direction of the line is written in component form as a, b, and c, where a, b, and c are real numbers, then we can rewrite the vector representation as follows. X, y, z, that's vector r. If you remember what we wrote on the last page, we said r was equal to r naught plus tv. So we're just going to make some substitutions now. R is x, y, z. R naught is x naught, y naught, z naught, plus t times v, where v is given by a, b, c. So therefore, we do a little bit of addition and scalar multiplication here. We get x naught plus tv, y naught, I'm sorry, x naught plus ta, y naught plus tb, z naught plus tc. So just distributing the scalar through to the second vector. And then in component form, if we were going to write this parametrically, we'll just go one by one. That means x is equal to x naught plus at, y is equal to y naught plus tb or bt, and z is equal to z naught plus t times c, or c times t. And t, again, is just any real number. So let's take a look at an example here. Find a vector equation and parametric equations for the line that passes through the point 5, 1, 3, and is parallel to the vector I plus 4j minus 2k. Okay, they're giving us a point on the line, so let's make that our p naught. So this would be our x naught, y naught, z naught. Okay, they are giving us a vector that is parallel, so that gives us our direction vector. Okay, so we'll make our direction vector 1, 4, -2. Okay. So if we put the vector, let's do vector equation first. Okay. Our vector equation, r, is going to be given by the r sub 0, which is going to be the vector created from the origin out to the initial point, 5, 1, 3, plus the direction vector is given by 1, 4, -2, and so we want scalar multiples of that direction vector. So we're going to take our scalar t and multiply it by that direction vector, 1, 4, -2. And so if we simplify, we end up with 5 plus t, 1 plus 4t, 3 minus 2t. So that would be our vector representation of the line. If we were going to write it parametrically, then we would have x is equal to the first component, 5 plus t, y is equal to the second component, 1 plus 4t, and z is equal to the third component, 3 minus 2t. And in this situation, since we're graphing, or not graphing, but since we're writing the equation of the entire line, t can be any real number that we choose. We will see that when we want just a line segment that starts at one point and ends at another point, we have to restrict that value of t just a little bit further. So in this case, sorry, technology's glitching just a little bit. There we go. Okay. We don't need to necessarily write this, but if you want to clarify, this just means t is an element of the real numbers. That just means t can be any real number that we want. Okay. If you don't include that, I won't take off for that. And then they might ask you, find two other points on the line. We already know this point 5, 1, 3 was on the line. So how do you find other points on the line now that you have the equations? You just pick different values of t. When t equals 0, we end up getting that 0.513. So let's just pick a different value of t. You can pick whatever you want. I would just try and keep it simple. Let's say t equals 1. Then you're going to end up getting 5 plus 1, so x will be 6. Y will equal 1 plus 4, so 5. And z will equal 3 minus 2, so 1. So another point on the line would be 6, 5, 1. Pick another favorite number. I like the number -1. And you don't have to use these two. You can use any two numbers you want. If you do that, you would get 4, -3, and 5 if you plug them in to either our parametrics or our vector equation. So we end up with... Now notice I'm doing ordered pairs now because it said points, not vectors. So I'm not using brackets. I'm using parentheses. Just a small little detail to make sure that you're careful with. Okay, so that's 2 other points on that line. Notice the vector equation and the parametric equations, they are not unique. There is obviously more than one representation you can use to write the equation of the line. It depends on what you consider the initial point to be, and it depends on what you consider the direction vector to be. Had I chosen the point P naught to be 6, 5, 1, well, then I wouldn't have seen a 5, a 1, and a 3 up here. I would have seen a 6, a 5, and a 1, right? So it depends on what you consider your P naught to be. Could have chosen that to be the initial point. And I didn't have to use 1, 4, -2 as my direction vector. I can use any scalar multiple of that direction vector. So what if I had used 2v as my direction vector? So then I would have had 2, 8, -4. Well, then my parametric equations, if I use this as my initial point and this is my new direction vector, then I would have x equals 6 plus 2t, y equals 5 plus 8t, and z equals 1 minus 4t. Okay. And what you'll see if you were to graph this, it's the same line. It's the exact same line that we had up here, but I'm using a different initial point and I'm using a scalar multiple of that original direction vector. So it's still going to give me the same line. It's just going to, it's going to map those original points to different spots on the line. Okay. Another form you're going to be asked to write the equation of is what's called symmetric form of a line. This is just when you eliminate the parameter t. So if you remember what we had before, we had x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. That was the parametric form of the line. If I solve for t in each of these, it's the same t. Whatever t I plug in here has got to be the same t that I plug into the other two. If I solve those, what I end up with is I get this equation. I get x minus x naught over a equals y minus y naught over b equals z minus z naught over c. All of these are just saying t equals t equals t. Okay. This works so long as a, b, and c are not 0. I can't divide by 0. And these are called the symmetric equations of the line. Okay, so let's try this. Find parametric equations and symmetric equations of the line passing through the points 2, 4, -1, and 5, 0, 7. So they're giving us 2 points on the line. I'm going to choose A to be my initial point. You can choose either. So I'm going to let this be my P naught. Okay. So then my direction vector, I'm going to move from A in the direction of V, or in the direction of B. So my direction vector is going to be given by vector AB. Subtracting, I get 5 minus 2 would be 3, 0 minus 4 would be -4, 7 minus -1 would be 8. Okay. Just subtract those components. Okay. R sub 0, right, would be given by 2, 4, -1. So R, my vector equation of the line, would be given by the initial vector, 2, 4, -1, plus scalar multiples of that direction vector. So t times 3, -4, 8. And so my parametric equations, that's what they asked for in the problem. Got to read the directions here. Would be x equals 2 plus 3t, comma, y equals 4 minus 4t, comma, z equals -1 plus 8t. T can be any real number. that we want. Okay. And then again, you can, from there, if you already have the parametric, you can just solve for t, or you could set it up from scratch, even if you didn't have the parametric equations. The symmetric equations, look back up at the top of the page if you need to. It's x minus x naught over a. Well, here's our x naught, here's our y naught, here's our z naught, so we got to flip the sign. X minus 2 over the x component of the direction vector was 3 equals y minus y naught. Y naught was 4, so y minus 4 over the y component of the direction vector, so over negative 4, equals z minus z naught. Z naught was negative 1, so we'll get plus 1, z plus 1, over the z component of the direction vector, which was 8. So notice here it's an equation. It's not comma separated list. Okay. So that describes the line 2 different ways. Okay, on a quiz or a test, you got to know this vocabulary. I'm not going to give you those equations. So you need to know what parametric means and what symmetric means. Okay, a follow-up question. At what point does this line intersect the XY plane? You don't really need a visual here, but it might help. Here's your XY plane down here on the ground. Let's just say the line looks, something like this. The point where it intersects the XY plane would be the point when z is equal to, see if you can think about that on your own for a minute, should be z equals 0. So all I really need to do is take my equation for z, and I need to set it equal for 0 and solve for t. And then I can plug it back in. So first thing I'm going to do, I'm going to take my equation for z, negative 1 plus 8t. I want that z coordinate to be 0 down here in the xy plane. And I'm going to solve. Add 1, divide by 8. I get that t needs to be 1/8. Now, I'm going to go back up to my equations for x, y, and z, and I'm going to plug in 1/8 in for t. So x was 2 plus 3t. We know that in the xy plane, t is 1/8. So I get 2 3/8, which would be 19/8. And then if I do it for y, we already know z is 0. That was the whole point of doing the xy plane. But we need the y coordinate. Y, if we look back up, was 4 minus 4t. So 4 minus 4, still letting t equal 1/8 at this point right here. 4 minus a half would be 7/2. And we know that z is 0. So therefore, the line intersects the xy plane at the point 19/8, 7/2, comma, don't forget the third coordinate, which is 0. Okay. And that would be this little point right here. Okay. Last page here. Find parametric equations for the line segment, so not the entire line, the line segment, joining the points P and Q with ordered pairs given. So remember, now we're not extending the line infinitely in both directions. We have a specific starting and stopping point. Okay? We want to go from P to Q or from Q to P, whichever way you think about it. So we're not going to be able to let T be given by any real number anymore. Otherwise, we're going to get the entire line. We have to somehow find a way to restrict. So what you should be thinking here, the big question is, how do we restrict our parameter T? We're going to have to restrict it now so that we start and stop at this point, at these 2 points. Writing the equation of the line is the exact same way that we did in example 2. Okay, so it's the exact same points I gave you as we had in example 2. So I'm just going to put from example 2. If you need to go back and take a look, do that. Our direction vector was given by the difference of those components. So 3, negative 4, 8. Okay. And our parametric equations were given by x equals, I chose to start at P when we did that example. So 2 plus 3t y was equal to 4 minus 4t, and z was equal to negative 1 plus 8t. And in the example 2, we said t could be any real number. Well, we have to be more strategic here. Before we had the whole line, how do I specifically choose values of t so that I'm only restricted to this red portion going from p to q? Well, it's just a matter of, kind of trial and error. What t value would start you at 2, 4, negative 1? See if you can think about that for a minute. Okay, so hopefully you notice that when t equals 0, we end up getting the point x equals 2, y equals 4, and z equals negative 1. Well, that's exactly point P. Okay, so that's good. We already know that t equals 0 has to be part of our restriction. And what would be our stopping t value? So we know we can start when t equals 0. Where do we stop? Well, we want to stop at 507. So you have to figure out what you need to plug in for t so that you end up getting 507. If you try some numbers out, you'll notice that it's when t equals 1. So when t equals 1, x equals 5, y equals 0, and z equals 7. That's exactly point Q. So that'll give us the line segment from P to Q if t ranges from 0 to 1. So all we need to do, write our final answer. The line segment is given by, so I'm going to put our final answer in this blue box right here. X equals 2 plus 3t. Y equals 4 minus 4t. So it looks almost exactly the same as what we had in example 2. Z equals negative 1 plus 8t. But we need to specify 0 is less than or equal to t is less than or equal to 1. Make sure you include this. That's what makes it a line segment. Okay? This would be what represents segment PQ. Okay? This right here. So on a test, I would need to see this restriction if it asks for a line segment to get full credit. If it just asks for the line, then you don't need to include that. Any real number would represent the line. Just another way of doing this. This is my process. How we did it in example 3 is exactly how I would do it. But your textbook does give another representation. If you want to write the equation of the line segment from a starting point to an ending point, well, you can draw an initial vector to the starting point. You can draw a final vector to the ending point. So we'll call those vectors R0 and R1. Then the vector equation would be given by R of t equals the vector going to the initial point, so it'd be R0, plus t times the direction vector. Well, that was just the difference in the coordinates, which would be the difference in the two vectors to those coordinates, R1 minus R0. This is exactly what we did here, just in symbols. And what your textbook does is they simplify this. So if you clean up the algebra a little bit, this is the same as 1 minus t times R0 plus t times R1. This is really how I usually do it, and that's how we did it in example 3. I'm going to put a star here. Some people like to just jump directly to this. That's also fine. Okay, so if you want to write the line segment, you're welcome to do that as well. Okay, last question. One to make us think a little bit. They give us a pair of lines. L1 is given by the components x, y, and z using parameter t. Line 2 is given by the components x, y, and z with parameter s. They're just using two different variables for the parameter here. One thing I'm going to do is I'm going to write these in vector form because we're going to want to look at the direction vectors. Okay, so I am going to write these equations for L1 and L2 in component form, so off to the side. So this would be 1, 5, negative 1 plus t times 4, negative 4, 5. And you'll see why I'm doing this when we get to the question down here. Second one is going to be 2, 4, 5 plus s, that's my parameter for the second line, times, I factor an s out, I'm left with 8, negative 3, 1. I'm going from parametric form back to vector form. And the reason why is so I can see those direction vectors. So let's look at what they're asking. They want us to decide if the lines intersect, if they're parallel, or if they're skew. First thing I would do in a question like this. First thing I would do is actually make sure I understand what the vocabulary is asking. Intersect means they cross in a point. Parallel would mean that they don't intersect, but they're actually in the same plane. And skew, it's probably been a while since you've seen this term from geometry class. Skew means they're also non-intersecting. So just like parallel, they don't intersect, but they are non-coplanar. So they are not in the same plane. And so what that would mean is either their x, y, or z coordinate differs while the other two coordinates might remain the same. Easiest visual to look at this as a box. Probably back in geometry class, you remember this? Maybe you got some line up here. Maybe this is L1, but then maybe way down here underneath, you got L2. So they don't cross, but they're moving in different directions. You got one way up in the top plane, and then you got one way down on the bottom plane. I always think about like a car that's driving underneath a bunch of railroad tracks. So the car is going to move this way. The train up here can still move this way, but they're not going to cross, but they're on different planes. The train's way up here on the tracks, and the car's way down here on the ground moving under the train. And the cheesy way I always remember this is skew lines. Take a look at my visual if you can see me. Skew lines make you go, excuse me? Okay, notice they're not crossing, right? Excuse me? See how they move? Excuse me, skew, LOL. Okay, get the dance down. Okay? Do it at the homecoming dance. The excuse me dance. It's part of your homework. Okay, I'm done. All right, so how do we approach this? Well, first thing I usually do is I try direction vectors. So first thing I'm going to do is I'm going to check to see if the lines are parallel by looking at their direction vectors. And this is why I wrote L1 and L2 in their vector forms up at the top. I'm going to call V1 the direction vector for line 1. Looking up here, I can see that's given by 4, -4, 5. Looking at line 2, I can see the direction vector is given by 8, 3, -1. Okay. And if you don't want to write the vector forms, you could just look at the coefficients of t and the coefficients of s from the parametric forms. That will always give you the direction vectors. Okay, well, if they're parallel, think for a minute, what would I be looking for? I'd be looking for whether those direction vectors are scalar multiples of each other. That's how we decide if lines are parallel when we're looking at the parametric form. So I'm going to make a note here. The direction vectors in this case, well, the x value, if I go from 4 to 8, I'd have to multiply by 2. But then the other coordinates would have to follow that same rule. So if I looked at the second component, -4 times 2 should give me 8. But the second component here is 3. So not all of the components doubled in size. So these direction vectors are not scalar multiples. So what does that tell me? That tells me that these lines are not parallel. Okay, so I'm going to cross that out from my checklist. And now it's really just a matter of doing some algebra. If they intersect, we'll be able to find an ordered pair x, y, z where they cross. And if they're skew, we won't be able to find that ordered pair. So second thing we need to do is we need to check for an intersection. And so I'm going to organize my work here a little bit. L1, that's how I like to do it, is just make kind of little columns here. We've got our x coordinates, our y coordinates, and our z coordinates. We're hoping for a match where we can find an ordered pair where the x's match, the y's match, and the z's match. So line 1, it was 1 plus 4t, 5 minus 4t, and -1 plus 5t. We want our x coordinates to be equal. So we want x to equal 1 plus 4t to equal 2 plus 8s. We want the y coordinates to match, 5 minus 4t to equal 4 minus 3s. And we want -1 plus 5t to equal 5 plus s. Okay. How you solve this, I would just do some substitution. Is probably the easiest way. So pick x, y, or z and isolate either t or s. So I'm going to just choose x. And I'm going to write this. This would mean that t, if I solve for t, subtracting 1 and dividing by 4, I would get 1/4 plus 2s. Just a little bit of algebra. And then that t value needs to be consistent for y and z. It has to be the same t value for the other two variables. So all I'm going to do now is I'm going to substitute in 1/4 plus 2s in for t and y. So if I do that, let's see what we get. We get 5 minus 4 times t. We just said that t was equal to 1/4 plus 2s. So I'm going to sub that in. And that should equal 4 minus 3s. So let's see what we get for s. We get 5 minus 1 minus 8s equals 4 minus 3s. So we get 4 minus 8s equals 4 minus 3s. I'm going to add 8s to both sides and subtract 4 from both sides. So we end up getting 5s equals 0. So we actually get s equals 0. Okay. So when s equals 0, now we need to know what t is equal to. So we get s equals 0, which would mean if we plug back in here for t, if s equals 0, then t equals 1/4. And what you'll notice by doing that is the x and y coordinates are going to match, because that's what we just did, is we solve for t and s so that x and y are equal. So if we plug back in, if s is 0, we get 2 for x, and if t is 1/4, we also get 2 for x. So far it's a match. If we plug in 0 for s for y, we get 4 minus 0 be 4. If we plug in 1/4 for t, we get 5 minus 4 times a fourth would also be 5 minus 1, which is 4. So it looks like we're getting ourselves set up for an intersection point. These are where the two lines are going to intersect. All we need to do now is make sure that the z-coordinates also match for line 1 and line 2. Okay, this is the big surprise at the end of the movie. This is the big twist. You guys ready? No spoilers. Well, actually, there are spoilers because I'm doing the problem. But get your popcorn ready. Here we go. What do you guys think? Are they going to intersect or not? This is the climax of the movie. Okay, here we go. For line 1, z-coordinate is -1 plus 5t. T is 1/4. And we get -1 plus 5/4 would be 1/4. So on the first line, it hits the point 2, 4, 1/4. On line 2, let's see. We get z equals 5 plus s. S is 0. Uh-oh. We get a z-coordinate of 5, different height. So the x and y, the projection in the xy plane is still going through the point 2, 4. Problem is the z-coordinate's different. Okay? They share the same x and y coordinate, but they don't pass through the same height if I were to graph them. The first one has a z-coordinate of a 4th. The second one has a z-coordinate of 5. So what this tells me, because they differ in their z-coordinates, these points are not equal. So this tells me, therefore, the lines do not intersect. We already ruled out parallel because their direction vectors were different. So what I conclude, therefore, there's our therefore symbol, the lines are skew. Okay. And so that's how to approach a problem like that. A little bit of algebra, a little bit of recognition with the direction vectors, and that's it. Okay. All right. There's a second part to this section, but it would be too long of a video and too long of a handout. So I think we'll save that video and we'll look at equations of planes in the next part of 12.5. For now, you can get some start on your homework for equations of lines. Okay. Happy mathing.